Honors Physics. How you doing? So I am out today. I have jury duty, and you guys are going to have to figure all this stuff out on your own today. So let's take a look at our schedule for today. You're going to be working on some practice problems with our kinematics problem set that we've been looking at. The motion graphing practice that we started last time, you guys should just finish it up. And the acceleration concept, we're actually going to get into it. I'm going to introduce the concept with the slideshow here. Okay. So as far as homework goes, there is a Khan Academy that you could work on if you have time in class today, or turn it into homework. And then we're going to continue with the practice problems for 13 through 24. There is a link to the Khan Academy, and you've got your formulas handy here. Today's the day we're really going to get into using the formulas, so have those ready to go. Okay, so moving into today's lesson, let's take a look at questions 8 through 12. So for question 8, notice the graph here shows variation of speed with time. And it's asking you which graph show the distance traveled as a result of this right here. So as you think through a question like this, just notice that you have a slope right here for velocity, and that's showing you an acceleration. And just remember our activities we did before. What does acceleration look like on a position time graph? Right? Remember that whole idea of curves and such like that. So take a look at that. Be critical. See if your table can help you put an answer down on that one. Okay. Next one here is showing you an acceleration with respect to time graph. This is one of those graphs where you're going to be looking for a change of velocity, and that's actually the area under the curve. Notice that the time is bound up to 15 seconds, though, so you have to be careful about how you calculate that area. All right. Next one here. This one is showing you a graph with a velocity with respect to time graph, and it's asking you which of these things is true. Now, one thing I'll notice is that there is a slope for velocity here. So notice we have a high positive velocity. Slope is going down to a low positive velocity. Then it goes to 0, and then it goes to the negative velocity section right there. So just noticing that whole thing right there. But which of these things must be true if you always have a slope going on there? Okay. The next one here is showing you the displacement in time for negative acceleration. So what does acceleration look like? And especially when it's negative acceleration. And notice these are all showing you positive quadrants for position. So what does negative acceleration look like in that case? And then the last one here is showing you dropping a tennis ball off a roof. And in this case, we're thinking that gravity is in effect, but also friction. So as the ball gains speed, it's eventually getting closer to terminal velocity. That's this place where it stops accelerating and starts falling at the same speed. So which of these graphs do you think makes the most sense for that? All right, so once you've reviewed these with your partners and you feel like you've got a good place, go on to the motion graphs practice. This goes into your journal. We discussed this one last time, so I'm just going to let you guys do it, finish all the questions right here, and then go with your table into the acceleration lesson. So in this place, you're going to actually take some notes in your journal. Okay, and we'll start over here. So I want to notice that down in the bottom, I've got the notes, and these are the things that I would say in class and the things that I would point out in class if I was there. Okay, but notice right here, we have the formula for acceleration. It just says your average acceleration equals a change of velocity over time. And this is basically what we're referring to as sort of like the slope of a VT graph. So velocity with respect to time. When you have a constant slope, you have an acceleration being shown. And that's really what this equation is modeling. Now, one thing to notice about this equation is a simple equation of all, and it has velocity, it has that's final velocity, initial velocity, time, and acceleration all as part of it. We're going to do a lot of problem solving for acceleration just using that equation right there. So have that one handy. It's part of your formulas. Next one here is a fact to remember. Gravity is just another type of acceleration. We call it free fall. And with gravity, it's always negative 9.8 meters per second squared. It's directed downwards. Think if you have an object that's dropping downwards, the negative acceleration is going to accelerate the object in the negative direction, which is down. Also, the concept of weight is really just that gravity we just looked at times the mass of an object, mg. We looked at those with force vectors and when we did sort of like the weight of the tiger, things like that. Okay. Here's something to notice. If you were to take a ball and throw it up in the air and give it like an initial velocity in the positive direction, eventually the ball would have reached the top of the flight. It would stop for an instant. By an instant, I mean an infinitely small period of time. And then it would change directions and start falling downwards. Okay. Now, the question says, what would be the acceleration of the ball at all 3 points of the flight? So when you're going up, acceleration of gravity is actually directed downwards, and it's slowing the ball. Okay. When you're stopped at the top, you're actually not really stopped. You're just instantaneously transitioning from going up to going down. And at that point, the ball is still having its velocity redirected from one direction to another. So actually, you are, even when you're stopped at the top like that, you're experiencing gravity pointed down at negative 9.8 meters per second squared. And then as the ball is falling, the negative acceleration is accelerating the ball in the negative direction. And again, 9.8 meters per second directed down. In all cases right here, the acceleration is just g, or 9.8 meters per second directed downwards. Okay. Some people confuse it thinking, oh, at the top of the flight, the ball stops, so the acceleration must be 0. That's not true. It's always negative 9.8 meters per second squared. Now, there is an effect of air friction. This is an example, like if you were to launch a projectile on the moon, it would follow this nice symmetrical parabola. But if you were to launch the same projectile on the Earth, the right-hand side of the parabola would be truncated or shortened because of air friction. So air friction is actually constantly slowing the velocity of the ball, and it's going to affect its flight like that. Now, in physics, when we start getting into formulaic solving of problems, pretty much all the problems that we're going to do that are quantitative in nature are going to be assuming there's no air friction. Okay. Now that's an okay assumption when things are traveling slow, and a lot of like what we do in labs in class, we will be going slow, so it's okay to do that. But that's just sort of an idealization. We won't be actually calculating with friction quantitatively, but we'll ask you questions qualitatively about what friction would do to motion. Now, remember that the two slopes that we've been dealing with here are the slope of a dt, which we call velocity, and the slope of a vt, which we call acceleration. So as far as formulas go, we're going to get into formulaic manipulation now instead of just graph manipulation. Just see how these two things connect to these graphs right here. And this is a really important formula for velocity. This is a really important formula for acceleration. Okay, so we just keep coming back to those. Now, noting acceleration, what we call average acceleration, is just the slope of a VT graph. And if you wanted to take instantaneous acceleration off some sort of a curving VT function, you could take a instant slope. Okay, sometimes we call that a tangent slope. Or in calculus, you could actually find the function for that curve and then take a derivative from that function. So we won't do the calculus thing yet, but we will introduce it at some point. But anyway, notice the difference between average and instantaneous acceleration. Okay. Now, when we look at a graph of acceleration with respect to time, this is an AT graph, we can take the area under the curve in order to figure out the acceleration of the buggy. To figure out the change of velocity of the buggy. So with your partners, go ahead and do that. Notice that there's 3 sections right here. And let's just assume that the buggy started from velocity 0. And so any change of velocity that would occur would just add on or subtract from 0. Okay. But notice how you have a rectangular section, acceleration with respect to time. You have a triangular section. These are both in the positive part of the graph, and this is in the negative part of the graph. So actually talk with your partners and see if you can agree with an answer right now. What is the change of velocity of the buggy, which would also be the final velocity of the buggy? So talk with your partners and figure it out. Now, that idea of the integral actually leads us into one of our most popular physics kinematics equations. I'm just going to show you how that works. So notice this is a velocity with respect to time graph. And what we're seeing here is you have some sort of initial velocity and a final velocity. And the object in concern here is actually starting at a non-zero initial velocity. And then it accelerates. That's what the slope represents. And it gets up to some final velocity. Now, if you wanted to know what the displacement of the object is, you could take integrals or areas and add them together. And so I noticed like this area here, it's a rectangle. And generically, this would just be u, initial velocity, times t, time. So that section is called ut. You can kind of see that right over here. The other section would actually be the change of velocity, v minus u, times t. Right? So you can see that v minus u times t, and that would be divided by 2 because it's a triangle. And so that would actually look like v minus u over t. Now, if I were to then just go ahead and substitute from my equation for acceleration, remember acceleration equals change of velocity over time. So I can just take acceleration as change of velocity, divide my time over to the side, say acceleration times time equals change of velocity. I could substitute integral. I take away the v minus u and replace it with at. And that's how I end up getting this whole ut plus 1/2 at squared, which is one of our physics equations. And notice how this is modeled as the quadratic equation. Again, down here in the bottom, I've got an explanation of that. Okay. All right. So now we've sort of seen, we've got these physics formulas. How do we deal with them? So we're going to follow this practice problem solving format. And in the format, you're going to want to go ahead and start many times, not all the time, but a lot of times with an actual drawing of your situation. And sometimes you're going to be using free body diagrams with that too. Now, once you have decided, okay, here's the situation I'm dealing with this problem, you're then going to go ahead and pull out all the known variables out of the problem. And then with those variables, you're then going to ask yourself, what are the unstated known variables? Some of the things that they often don't tell you that you should know are gravity is operating whenever something is in free fall or being acted upon the air being thrown or something like that. And gravity is just the acceleration is negative 9.8 meters per second squared. Sometimes they'll say something like a ball is thrown up in the air and it gets to the top of the flight and then starts falling. You might know the speed that you threw the ball up in the air with, but it doesn't tell you that the ball will be zero velocity at the top of the flight. But you should assume a ball will hit zero velocity when it gets to the top of the flight. Okay. Sometimes I'll say things like the cart starts from rest. Well, that's your initial velocity is zero. That's what starts from rest means. So you should be able to then hit those pieces, bring those into the known variables you have, and then find out which variable a question is asking you to solve for. And with that variable, they label it as a question mark, and then you're going to find a physics formula that works for you. You're going to go ahead and solve algebraically just for the unknown variable. And then after you've got something like t equals v minus u over a, so you've solved just the unknown variable, then you do what we call plug and chug, just throw the numbers in and solve the problem. Okay, so that's kind of the format that we're going to work with now. So here are your physics formulas. Okay, so we're going to be using these extensively. This one here is change of position is equal to your average velocity, which is your initial and final added together divided by 2 times time. Okay. Notice acceleration is missing in that problem. The next one is our quadratic formula. We just worked that one out with the integrals where I showed you how we developed that one. But this one says your change of position is equal to your initial velocity times time plus 1/2 at squared. Now, oftentimes you're going to substitute a right there with gravity, because gravity is what the acceleration is when you're throwing a ball up in the air or something like that. Now, this one is missing your final velocity. Notice that. Now, this one here, this is they call the timeless equation. It doesn't have time in it, and you're going to go to this one quite a lot. But it says your final velocity squared is equal to your initial velocity squared plus 2a change of position. And then your last one here, acceleration is equal to change of velocity over time. And sometimes you can work that out by saying final velocity minus initial velocity divided by change of time. Notice that it's missing position. It doesn't care about position. Okay, so those are the formulas, and you're going to be using this formula format to solve these formulas. All right, so go ahead and practice this now. So the first video you're going to look at today, I want you to calculate the acceleration of this airplane. And in this case, it's actually going to be a negative acceleration in the sense that it's slowing down. So what you'll do is you'll play the video. You're going to see that the airplane is coming in for a landing. And right when you see the airplane hit the ground, I want you to use your phone, start timing how long it takes for the airplane to get to the point where it's basically stopped and it turns. Okay, it's not actually going to make a complete stop, but you have to just kind of like time it from touchdown to when it looks like it's basically almost stopped. Okay, and let's just call that the airplane landed at 55 meters per second, and we'll say that it's going 0 at that point. Get your time, and then go ahead and use your formula for acceleration as change of velocity over time. Calculate the acceleration of the airplane, and you should notice that it's a negative acceleration, which is basically deceleration. Now, once you have that, go ahead and use your kinematics formulas and find a formula for displacement, and then find out, well, based on that acceleration and based on the amount of time that it went through, or whatever other variables you can get, velocity, final or initial, okay, you could manipulate different formulas for position. I'm going to notice that there are 1, 2, 3 different formulas per position there. Okay. Then come up with the displacement. And notice down in the yellow, I've got everything worked out for you so you can check your answers. But do this with your partner so you can kind of mess with it together. You're going to do the same thing for this airplane. This airplane is going to take off from a start. So this will be a positive acceleration. But given that this is an F-14 Tomcat, you're going to see that the time for takeoff is very much shorter, which is going to affect the acceleration and the displacement also. Okay. Now, once you've done that, pick any old random section of this motorcycle going through an acceleration. So just watch the speedometer on the right-hand side. And when you see it like rapidly increasing or rapidly decreasing, pay attention to the speeds and notice the speed change over a period of time that you'll time, and you'll calculate the acceleration. But you're going to notice that your units for acceleration are in kilometers per hour. That's what this reads on this per second. Now, to do a conversion to meters per second squared, 1 kilometer per hour per second is actually equal to 0.28 meters per second squared. So do a conversion and then figure out the acceleration and then the displacement that the motorcycle would have done during that time frame. Now, notice the displacement is going to be different than before because you're actually having an initial velocity and a final velocity, which are not, one of them is not zero. So you got both of them are some significant number. So that's going to change your displacement there too. So now once you've practiced those calculations, you're then going to go into the kinematics practice problems. And with your partners, you're going to do 13 through 17. And as you take a look at these, you're going to notice that, let me get down here for you. You have your problem solving format right here. You got to use that when you're solving these problems. You got your formulas right here. And you've got your key to the answers, okay? So for 13, 14, 15, 16, 17, I want you to talk with your partners and work through this and get those done, and we'll check them next class. So that's it today. You guys have a great day. I'm at jury duty today, so have a great day. So I'll see you later. Bye.